I would like to introduce our keynote speaker for today, Kireeti Kompella, who will be presenting Network Digital Twin. Kireeti is SVP and Chief Engineer for the AWAN business unit in Juniper Networks. Dr. Kompella was formerly CTO at Contrail Systems, and before that, CTO and Chief Architect at Juniper Networks. His current passion is to develop the self-driving network. He has been working on WAN automation as part of the Paragon Automation team. His focus is highly customizable, intent-based service orchestration systems with intelligent service placements. Welcome to the stage, Kireeti.
Hey, everyone. First of all, many thanks to the committee for accepting my proposal and inviting me here for a keynote. Yeah, so I did speak here once before, actually twice before. Once was in NANOG 23. NANOG 23, anyone? And thank you. I made a presentation. I used this particular template in classical ball player superstitious mode. I'm going to use the same template because I think the other one was received well. So maybe this will be. I don't know. Who knows? There's been a few changes from 2001 to now. Our logo changed. There's a small change in my title. What's it called? Aspect ratio changed from 4:3 to 16:9. So I had to make that change. The rest just works. Okay, so I'm going to talk about network digital twin. So let's just get started. This is what I had back then. Not exactly the same content, but I decided I'm going to start this off as a menu. I'm sorry you don't get customized menus, each of you. You all will get the same thing. Okay, so start with the definition. So I went to IBM, HPE, and Wikipedia and said, what is a digital twin? And there are a lot of similarities in the definitions. Virtual, simulation, a little bit about machine learning, and then the Wikipedia one goes into other things like integration, testing, monitoring, maintenance, and we'll see all of those play out in this thing. The term digital twin was, as far as we know, first coined by John Vickers of NASA. So what we're doing now is rocket science. It's actually not a bad thing because putting a rocket in space is really expensive. You don't want to say, oh, I'll do it again. I know SpaceX takes that particular approach, but in general, you want to get it right the first time. So as much as you can do testing ahead of time, I think that's a good thing. And then for you guys, putting stuff in the networks, you want to get it right the first time as far as you can. So maybe this will help. Okay, so let me, I have a cough, so I'll try not to cough into the mic. It's not an infectious cough. Well, I don't know. I'll be spitting on you, so stay far away. But, so I'm going to start with automation, and I'm going to take a very naive approach to automation, just to make a few points. Automation, you can essentially say it's about making humans more effective, enhancing human capability. So if I gave you a shovel and said, go dig a hole, you might take 8 hours to come up with a pretty nice sized hole. But if I give you a bulldozer, you could do so many, you'd never stop making holes. So that's a whole different problem. The other thing that automation does for you is reduce human error. So if you say, here's the sequence of steps that I need to do for a certain process, like I want to upgrade my router, so here are my steps. So you can write those down so that every time you upgrade the router, you're going through the same steps. You might find some errors. So the errors that you anticipate or that you've seen, you can then code them into your script. And so the next time you do it, you watch for certain conditions and say, yeah, I'll do it better this time. But in the process, can it find new errors? Can it actually fix them? And the answer is typically not. So maybe we need something more than just automation. So the stuff that you've thought through, this is the straight line automation where you're basically saying, I'm going to go through these steps. You could have branching. You could have simple loops like, I want you to do this for these 10 devices or these 50 devices. But things that you anticipate, you can code into your script. Things that you don't anticipate will always surprise you. And the thing about automation is it magnifies your ability. It also magnifies your mistakes. So if you did something stupid to one router, yeah, it's bad. But if you had an automation script and you hit the button, your network went away. So is automation sufficient? It leads to this thing that if I have this straight line thing that I want to code, it's easy-ish. But you can't anticipate all possible errors. And you can't, at least not in a straightforward way, anticipate or try to figure out what the root cause of an error is. And when you then get to automatically fixing it, life gets very, very complicated. So maybe you need more than just straight-line automation. What is now called closed-loop automation or closed-loop operation. So we'll get to that in a second. Testing is another important thing. You want to be able to test things as much as you can. So you can't, for code in general, you can't prove that a code is bug-free just by testing. But you can reduce the probability of bugs. So like I said, you can anticipate a few, you can try it out and find a few more and fix those. And so the nice thing about coding it is whatever you've learned, others can benefit from. So how does testing typically work? There's unit tests, I'm going to leave that out. There's functional tests that says, does the code do what it's supposed to do? And then there's regression tests say, oh, fine, it does what it's supposed to do, but what did it break? And these are typically small-scale tests. You might just run it on your laptop. You do a few things. So there's black box testing, there's white box testing. So that's there. Then you have scale tests and real-world tests. So scale tests say, let me try this not with 2 or 3 boxes, but with maybe 50 or 100. It gets hard to do, and getting all those resources is difficult. Real-world tests is I'm trying to set up a network that mimics an actual provider network. I'm going to run multiple things, not just the thing I'm trying to test. In that case, you find a lot more bugs. And so these are important, but they're much harder to do because you need a lot more resources. But the scaling tests and the real-world tests also find the most bugs. I'll tell you a story. Back when I was actually an active coder, which I haven't been for a while, we'd get a QA, you'd write up some code, stick it into JunOS, and some QA guy would say, okay, I'm going to have this configuration to test this particular piece of code. And they'd run their tests, and it seems to be okay, and then they leave the thing that way. And the next guy comes around and says, oh, the test bed is free, I'm going to do my test. And so they have a config that they want to do, and they do load override, commit, and it blows up. And you find more bugs. You're trying to find bugs in this new code. You find bugs in doing the load override. I hope it's still not the case, but who knows? Code is code. So the point is that functional tests and regression tests are important, but these other tests are so much more important. And part of the real-world test is also what we call longevity tests. So do you have a slow memory leak that you won't see over the course of an hour or a day or even a week? So we try to run the longevity tests for several weeks or even months. Okay, AI. Oh, our problems are all solved, maybe. So AI can help. And for example, you might say, I want to find anomalies in my network. So you write your favorite Python script, and you say, grok through all the configs on all the boxes and see that MTU is the same everywhere, because that's a silly mistake that happens quite often. It's a Python script. You want to call it AI, I'm not stopping you, right? Or you might say, I'm going to get all this telemetry from my devices, and I know that between 10 and 11 on a Tuesday morning, traffic is typically between 10 and 50 gig, right, on this particular link or on this LSP. And so you can get that from statistical analysis. And again, you feel free to call it AI. Okay, so this is where you're at. But today, for some reason, traffic is at 2 gig or at 99 gig. And why did that happen? So you want to find the root cause. Finding the root cause is typically not something that you can just whip up a Python script. So maybe you can use ML techniques for that. And once you've found the root cause, or at least a potential root cause, you might say, oh, here's something you might do to fix it. And so that's another thing where actual ML can come in, and machine learning can come in and do things for you. So here's where machine learning actually will help in your network. So this is great, except for most machine learning techniques, you need lots and lots of data. So remember those scaling tests and those real-world tests? They will give you lots of data. And so maybe you want to use those, leverage those, so that you can get the data that you need for your machine learning operation. But are you going to do that in your real network? I don't think so. The other thing is, how often does a network actually break? Well, hopefully not too often. I'm sure you say that it breaks more often than I want it to, but not necessarily in the way you want it to break, because you want to train your machine learning algorithm. So how do you create a controlled situation where you can get the type of breaks that you want to learn and find the root cause for and find remediation for? And then how do you recreate a situation if you're trying to debug it? So you want to figure out what happened, recreate the situation, debug it, say, now I have a fix, try it out. If you can recreate the situation, you can then say, yeah, this fix worked or it didn't work. So finally, we get to digital twin. Only took 15 minutes. So a digital twin allows you to clone your network. So you can recreate a problem, you can try out fixes. But for me, the best part is, you're now looking at this timeline. You can say, what happened yesterday, a week ago? Something went on in my network. I want to figure that out. It's already gone, but maybe you can put that in a digital twin and say, let me grok through syslogs and grok through rib states and try to find out what happened and why it happened. You can look at the present, what is happening right now. And the best part is you can look at the future, and you can look at all these different types of futures. Think multiverse, right? The probable, the possible, the never to be, but maybe it's still interesting. You can do all these things on a digital twin that you can't do in a real network. So let me sort of get into what is a digital twin. It's a clone of your network as is that captures the connectivity, all the topology, all the connections between all the nodes and the links. So it's a graph. Except the node is not just a vertex in a graph. It is running the full operating system that you have, the full software, as much as you can, that you have on your box, so on the node. The control plane, the management plane, APIs. So if I want to write an automation script that says, send these netconf commands to my box, and based on that, configure a VPN, I can do that because the nodes in the digital twin have the APIs to do that. And to the extent that you can, the data plane. So if you can emulate the data plane that will actually run on the box, really good. We have a particular family of chips that have microcode, and we can literally run that microcode in the virtual image. For others, we don't have it or we don't have license to use it. There is a simulator, but we don't have access to it. But when you do, it makes it even better. So the nodes and links are virtual, and the node runs the same OS control plane and management plane as a real node. So it allows you to do a lot of things. So you've captured your network, but now you have these external things, like you have peers connected, you have customers connected, you have various connections coming into your network, and they're sending you traffic, they're sending you routing. So you can simulate that via this traffic generators and route generators. So if you can not only capture the state of your network, so you're capturing the connectivity, the configs on all the boxes, the OS is running, but you also capture what is the traffic at that point of time, or what is the traffic in the last 24 hours. You can even play that through. So a lot of words on the slide. I think there's a lot of things you can do with a digital twin, but I'll just focus on two. Education. So you have a new NOC engineer, and you can give her here's a VMX, go play, right? Or a V, whatever, your favorite device. And so she can get experience provisioning a router. But you might say, no, I want you to look at enough routers so you can understand how an ABR operates. So you need some routers on this side, some routers on that side, and you need the ABRs. Okay, now I want to get even fancier and I want to do multiple ASs. I need more and more stuff. So you may have a lab available that you can say, go play there, but typically that's a resource that's going to be overused, oversubscribed. If you could just bring up a digital twin and say, okay, you've done lesson 0, lesson 1, lesson 2, let's get to lesson 7. Here is the digital twin. I want you to, set it up with multiple areas and multiple BGP families, and et cetera. The other thing I think that you can really do in a digital twin that I think is really cool is experimentation. You guys have a network to run. That's not a network you can play in. And so you tend to be meaningfully, it makes total sense, very conservative about what you do in the network. But if you could clone that network, you could play. Like I say, you can go crazy knowing you're a reboot away from I reset everything and start again. So here's my opportunity to do these migrations that used to be quite common back in the day. It's all Vijay Gill's fault, going from OSPF to ISIS. Or I want to take all my different ASs that, there's an accretion of ASs because of this acquisitions that happen, and I want to now try to create a single unified network. Or whatever. You want to play with moving from VPLS to eVPN. It's like, do I get the same features? How does the RIB work now that you're carrying a lot more stuff in it? And there are other things. I won't go through there. In doing all this, one word that pops out at me is fidelity. How faithful is your digital twin, your clone, to the real network? And of course, you don't have hardware, right? So you've got a virtual thing. So how close is that? You don't have the same forwarding necessarily. So how close is that to forwarding in your real network? The closer you are, the better everything is, but also the more expensive it gets. So whatever you're interested in, whatever your sort of use case is for a digital twin, you can do a lot better if you get down to emulating things really well, but it's going to cost you a lot of money. So say you want a network of 500 nodes. You can create a digital twin that just captures management. So I'm going to use Juniper terminology, but you could have a bunch of MGDs running and say, I want to provision things, and I want to know if my provisioning works. Or I can have CRPDs that actually runs routing protocols. Or I can say I'll have V devices, and then I can get a little further. Or you can say, no, I want a physical network of 500 nodes. That's going to get expensive. So the point is that you can have different levels of fidelity, and as you go up the stack of fidelity, your cost goes up, but your results are much more meaningful. Benefits, there's a bunch of things. Whether it's for us, by the way, this thing that we call VMX was a testing tool that our QA people said, we want to build bigger labs. We can't afford it. We run out of space, power. We just don't have money as well. And you have this thing called VMX. It used to have a bandwidth of 10 meg. But that's good enough for sending pings and doing stuff. So it started off as a testing tool. And so whether it's internal to a vendor saying, I want to try this new code out and I want to see what breaks if I put it in a network of 500 nodes, or whether it's for you guys saying, I want to offer this new product, what would it look like? And so instead of sort of a wet finger in the air or just guessing, you can make data-oriented decisions by actually trying it out in a digital twin. You can experiment, as I just said, and then you can do efficiency. So if you say, if I move my traffic around this way, or if I do my load balancing differently, or if I do whatever these parameters in RSVP, what would happen? In fact, we have a tool that does if it's just traffic, but you can go much, much further, right? And you can say, I want to do more efficient XYZ, so you can optimize, measure, optimize, measure, optimize, measure. So in the digital twin, you could go crazy with instrumentation. So back when I was actually coding, we'd have this tension between providers and vendors. Provider says, I found a bug. Vendor says, can you please reproduce it? And then it degenerates to expletives. So, yeah. So it is important to be able to recreate the situation. It's not always easy. It's definitely not something that you can do in a real network. So if you could have a digital twin and then set up the situation that you thought might have caused a problem and then work through it and say, yeah, it does actually happen again, then you can instrument it, you can try to fix it, and then you can try out the fixes. And if it's on a single box, you don't need a whole digital twin. But if it's a situation where you have multiple boxes, multiple things happening together, then a digital twin would be a much better way of doing this. So that whole thing about can you reproduce it would go into can you fire up your digital twin and then reproduce it there. There's a bunch of things you could do with, if you had all this data generation that you can do of error situations and so on. So you can talk about predictive and proactive maintenance. So because you have enough data and you can actually work your way through all this, you can then train your machine learning algorithms to be able to learn situations, look at trends, say this is what's happening. Based on that, you might say, oh, if that actually happens, maybe I want to look at some ways of fixing it. Again, you could have the digital twin, if you did this all on a digital twin, say, let me look at how do I fix those faults. So the nice thing about a digital twin is, while it's a clone of your network, a lot of the environment around it is under your control. So you could say, I want to send these routes, or I want to do this traffic, or this traffic matrix. So then you can set up the situations that you want to be able to predict. So the takeaway is, with a digital twin, you have more control and fewer consequences. There's one consequence I didn't mention. It'll cost you money, but AWS is not cheap. It doesn't have to be AWS. So use cases, if you had a faithful replica of your network, what could you do? For those of you who know what Planner is, it's a planner on steroids. For those who don't, just ignore that whole thing. So it's a platform for testing, for training, as I already said. It's a platform where you could imagine, okay, this is where I go nuts, but imagine putting on a Vision Pro and looking at your network in a completely different way, absorbing data in a different way. Yeah, ignore that too. You can do what happened analysis. So you say, this is a situation that happened yesterday, and I had this outage or this congestion situation or something, right? Can I then bring it up in my digital twin and tell, sort of work through the scenarios and say, oh, yeah, this is what happened. Don't do that again. And then, as I said, there's a bunch of what-if scenarios you can look at. So if the network just grows as it is, what will traffic look like? What will routing look like? If I made this change, if I added this route here, this link here, if I change my BGP policy, under all these scenarios, what would happen? And again, you can test on a single box easily, but if you want to test network-wide, then maybe you want to do this on a digital twin. Imagine testing. You have this automation script that you want to play with, and so you do the usual Git thing, you snapshot it, and then you say, when you do the commit, merge, I think it's called in Git, you run the tests, but not only run the tests, unit test, functional tests, regression tests, you fire up a digital twin and you run the tests at scale in there. If it comes back saying great, then you deploy the code, the automation to your network. If not, it's like, okay, I'm going to try again. The last thing I want to say is, and this is where maybe the Vision Pro comes in, your network, if you ignore the bottommost layer, which is typically different boxes, from layer 3 on up, you have the same boxes, but they have multiple roles or multiple things they're doing in your network. So you've got the basic layer 3 stuff. You've got routing that sets up these routing adjacencies. Then you've got an underlay. So you've built up your underlay, and then you put services on top of it. And I'm kind of biased, and I think VPNs and MPLS services, but you got all kinds of services. So if something happens in your network, the idea that you can walk up and down this dependency graph is really cool. So if this link went down, which customers will be affected or which services will be affected? If that customer is complaining, what could be the root cause? Go walk down the tree and say, it could be the routing change. It could be that my layer 1 has done something funky. So the idea that you can walk up and down this tree, you could do this in a real network, right? But if you had a digital twin, then we could make it so much easier to walk and work through this and actually make changes and then say, I changed the underlay thusly, and what happens to services? Or I want this effect in services. Do I need to change underlay? Do I need to change routing? Or do I actually need to go and put more stuff in layer 1? So yeah, the dependency graph shows you the relationship between devices, routing, underlay services, and customers. And while it might be fairly obvious in certain cases, having that laid out in front of you and understanding that if I change this LSP, here are the customers that are going to be throwing darts at me, right? Or if I have this, this customer calling up and saying, the latency between these connections has really gone crazy, you could say it's probably an underlay thing, but it actually might be something in routing. It might be a change in BGP policy, right? So that ability to understand all of those relationships and see it maybe, I would like to say tactilely, but we're not there yet. The ability to point you to hotspots, here are things that you should look for because it will eventually become a problem. Root cause analysis needs a dependency graph because you got 50 alarms and it comes down to that link went down or that link had too many bit errors. So yeah, the dependency graph I think would be really cool. So yeah, finally I get to my conclusion. I think to take automation to the next level to really, get to the point where our automation is so much more effective. We need all these pieces like machine learning, smarter root cause analysis and stuff. But we need a platform where we can play with all those things. So I think as a community, we need to invest in a digital twin. So basically, digital twins continue the automation story. I'd like to say complete, but there's no end to it. So you got automate, you got test, and then you can say, fire up the digital twin and check out things. Now that you have your digital twin, you can do real world and scale testing and so on. But you can also do ML training and say, oh, these are all the things I'll learn from the network. And when you have the tests, if they fail, you can say, okay, here's what I need to debug, and go back to automate and close the loop. So, like it said at the beginning, I think the end of all this is a network that runs itself. And just like the self-driving car is just around the corner, so is this one. But I think we should continue making steps in that direction. And a digital twin, I think, is a concrete step we can take in that direction. And I think it has a lot of benefits anyway. But maybe in the end, it'll help us with this predictive stuff and the closed loop operation, which are all elements that you need for a self-driving network. Okay, so this was in my slides, slightly updated from 2001. Hasn't changed much. Well, I added unreasonably idealistic because I just am. And I've always been, I think, reasonably agnostic. I did want to once start singing Losing My Religion on stage, but I realized there'd be mass exodus, so I didn't. But that was what was going on in my head. Okay, questions? Clear as mud. Go for it.
Online question, Matt Petach, unaffiliated. Great talk. One of the big challenges with AI models is ensuring fidelity, the hallucination problem with LLMs, for example. Do you have any heuristics or techniques for evaluating a digital twin to ensure it's faithfully reproducing the exact state of fidelity of reality? Or do you just cross your fingers and have a blind faith that no anomalies have crept in during the population of the digital twin?
Yeah, I'm not a cross your fingers and hope kind of guy. So I said ML. I didn't actually say Gen AI for a reason. I think Gen AI will get better, and I think hallucinations will reduce. And the whole thing about Gen AI is, LLMs, is they've been trained on all kinds of crap. And so especially if you look at ChatGPT or something, it was trained on everything that's in the internet. So this big vacuum sucking up everything. So you don't have good fidelity there. But if you do your training on a much better set, I think you can improve the outcome of LLMs and reduce hallucination. But I think knowing that those exist means that in your testing, did my Gen AI work? Did this particular machine learning work? You can say, does it reflect what's actually happening in the network? So if you were, for example, trying to do predictions, you could say, do some learning, try to predict what's going to happen, and then let this continue running and see if those predictions panned out. So I think that knowing that LLMs have hallucination problems and potential just making up stuff means that we can put in the things that will test for those. Digital twins don't directly enable that, but I think we can, in our use of digital twins, make sure that we do take those into account. Does that make sense?
Thank you. Second question.
Okay.
Steven, sorry, can't pronounce this last name. Has the network digital twin changed operations at Juniper over the last years?
Yeah, this is a hallucination of my own, so that's all it is right now. To be fair, we've been using virtual networks for a long time. Sistas uses it. Like I said, the first V device that we came up with was for Sistas or QA to play with things. So today we spin up topologies, we spin up things, and we allow people to, the testers will be able to test things. So if you consider that as a proto-digital twin, yeah, we do use that. We've been using it for 10, 15 years. But the full power of digital twin is not something we have done yet because we don't actually have it. But when we do, I think the first consumer, eat your own dog food, so we'll be the first consumer. Then we'll inflict it on the rest of you poor guys.
Thank you.